When we look for common denominators to serve as a multiplication when solving a rational equation, we can work with denominators that are more complicated, provided that we're able to factor them and look for any factors that they might have in common. We don't want to rush to just say, let's multiply all the denominators together and that's the common denominator. If you can factor them and simplify the expressions a little bit, it certainly makes the process for solving these a lot easier. So at first glance, you would say, well, these three denominators are all different from one another. I just need to say that the common denominator is all three of them. And the truth is you don't, because this denominator is one of our difference of squares, so it shares a factor in common with both of the other rational expressions, meaning our least common denominator, or LCD, is just going to be that expression itself, x minus 3x plus 3. That's the factor that we are going to use as the multiplication for all three of them to clear out all of the fractions. And fortunately for us, there's the overlap in the middle. So these two, well, we can say this larger expression for the common denominator is going to get multiplied there, it's going to get multiplied there, and it's going to get multiplied there. And remember the purpose of this. The purpose is to clear out all of the fractions. Sure, it's going to leave a factor behind, but the objective is to clear out all of the fractions, similar to the work that we did with complex fractions. So when that expression is multiplied by the three expressions in the equation, we're going to clear out the fraction in the first one and leave behind the x plus 3 factor. We're going to clear out both factors of this denominator because it matches the least common denominator perfectly, leaving behind the 8x squared. And then in the last one, we're going to do something similar to the first one and leave behind the factor x minus 3 because the x plus 3 simplified with the least common denominator. So as this expression went in to all three of those fractions, the first and the third left a factor behind, and that's okay. And the second one was simply just its numerator. The presence of the 8x squared in the middle is an indication to me from the beginning that we want to set this equal to 0. If there was no x squared term, we wouldn't necessarily worry about that. We would just be going through our normal linear equation solving. But the x squared tells me I'm going to set this equal to 0, and I'm going to hope that I can factor. So before we set equal to 0, let's get everybody multiplied out so the terms could all be moved and combined as necessary. There we get another x squared term created through that multiplication, and that's okay. We're going to combine him together anyway. Let's move all the terms from the left over to the right, combine everybody that we need to combine. And you can check me on this, but we should get 4x squared plus 6x minus 18. Now, the nice part about this being an equation is you would think, oh, I see all of these even coefficients and constants in this polynomial, I'm going to factor out a 2. Because it's an equation, instead of factoring out the 2 and then having the 2 just sort of hanging around, potentially getting in the way, you can just divide it away. Since 0 divided by 2 is just 0, we're allowed to just divide away that extra factor of 2, leaving us with a much simpler polynomial to factor. Careful manipulation of the AC method using the different techniques for factoring that we've discussed, maybe just a little bit of trial and error. We get that the factorization is 2x minus 3, x plus 3, leaving us with two solutions, x is equal to 1.5 and x is equal to negative 3. I leave the check of 1.5 to you. It does work if you do simplify or substitute it back in. There's just it's a little bit much with the arithmetic, but if you want to check it and convince yourself, you certainly can. It's actually a little bit easier if you write it as 3 over 2. The one that I want to discuss instead is the x is equal to negative 3. If you look back at our expression, our original equation, you'll notice that x is equal to negative 3 does not back substitute into that original equation in a good way. In fact, it back substitutes in a way that creates a division by 0. This is what we're talking about when we say an extraneous solution. This equation had an answer of x is equal to negative 3. But that does not mean that x is equal to negative 3 will necessarily work in the original equation. And that's because of the presence of those denominators. So it's incredibly important that you do back substitute. And this is going to be the most common situation that we're going to run into when we try to back substitute and it makes one of the denominators equal 0. Those are the easiest ones to check just to see if it happens or not. But it's never a bad habit to get into checking all of them and then seeing if that's going to happen.